Hello, and welcome to the last of the Conics sections, the Hyperbola. All right, so we've gone through a lot of Conics sections so far. We've done the circle, the ellipse, the parabola, and now it's time for the very last one, that of the hyperbola. So before we kind of jump into this formally, I want us to just kind of think about the progression, much like we did with the parabola. With our different cuts, as illustrated over here, this blue cut will generate a circle with only one focus point, that of the center. And then if we tilt that cutting plane a little bit, we get an ellipse with now two foci that are getting ever further apart as the tilt of the plane gets more and more, until you get this infinite open curve called the parabola that seems to only have one focus point. Now, where the other focus point went, it's not that it vanishes, it's just that it's infinitely far away. Weird things happen when we get to infinity. But then if we tilt the plane just a little bit more, because this green cutting plane that generates the parabola is parallel to the conic surface, if we tilt it just a little bit more, it's going to cut not just this bottom cone, but this upper cone as well. And so this cut that I've made, the brown dotted line is kind of the axis of that cut, generates two curves, two open infinite curves. So this is a lot of weird stuff. We go from one closed curve to one closed curve stretched out to one infinite and open curve to two infinite open curves. Now, this is kind of weird. If the hyperbola follows the same rules as the other conic sections, that is that it's defined by focus points, then it stands to reason that there's going to be one focus point down here in this lower part of the curve, and there's going to be one up here, which kind of answers the question that we were asking back with the hyperbola. What happened to that other focus point? It went infinitely far away, and then in a weird way wrapped around infinity, and then ended up back up here in the conic surface. If that's true, then that's kind of what would have to happen. Again, if the hyperbola does have two focus points that help define the curve. So there's going to be a lot of weird and interesting things about this. And we're going to get into what would an equation look like to generate a hyperbola. But before we take wild guesses, let's think about this. There is exactly one cut to generate a circle, right? At least in this case, right? And all circles are similar to each other. They're just different by a matter of size or scale. The ellipse, there's an infinite number of ways to cut this conic surface to generate an ellipse. So long as you're not parallel to the base or parallel to one of the sides of the axial triangle, you will get an ellipse. There's an infinite number of ellipses that one could cut into this conic surface. For the parabola, there's only one cut you can do. One angle, I should say. That is parallel to the side of the conic surface, which is interesting. And then we also proved that all parabola are similar to each other. So it's kind of interesting that the parabola and the circle have a lot in common. They are all similar to each other, meaning they just differ in a matter of scale. And there's really only one equation for all of them, right? Or one angle cut. I'm using those two phrases kind of synonymously. With the ellipse, there's an infinite number of angles you can cut the conic surface and generate an ellipse. And that seems to be the case with the hyperbola as well. Namely, once you are no longer parallel to the side of the axial triangle, there's an infinite number of angles that you can cut the conic surface such that you will generate a hyperbola, get both of those curves, one in the upper, one in the lower part of the conic surface. So it seems like the parabola and the circle have a lot in common, and that the ellipse and the hyperbola have a lot in common. The ellipse, you can cut, there's a lot of angles you can cut at to get an ellipse, and likewise with the hyperbola. with that being said, it might be a good idea to start with an equation for an ellipse and see if we can tweak it in hopefully a dramatic way so that we generate a hyperbola rather than an ellipse. Excuse me. All right, so obviously this is going to generate a horizontal ellipse, right? It's horizontal because the number under the x squared is bigger than the number under the y squared. So this is our b squared technically. It's going to have a major axis of 3 units, and it's going to have a minor axis of 2 units, right? Because the square root of 9 is 3, and the square root of 4 is 2. So we know this is going to get us an ellipse. What could we do to change it and pray that we get a hyperbola instead? Well, if we change the 9 or the 4, that's only going to affect how big or small the major and minor axes are. If we make this not 1, that's not going to change anything either. Again, that's just going to impact the major and minor axis because we can divide out that number, and then that's just going to affect how big or small the axes are. And we know that this is curvy in all directions, right? Because we're getting 2 curves, one is kind of like that and one is like that. If you were to transpose this lower one up here, we can see that it's going to end up being curvy in all directions, if you'll allow me to talk that way, much like a circle, right? That's how we kind of came to discover that the equation for the circle, both x and y are going to have to be squared because it's curvy in all directions, unlike the parabola where only one of the terms is squared because it's only curvy kind of in one direction. So the hyperbola is going to be curvy in all directions, so we're definitely going to have x squared and y squared. We can't touch, or changing these numbers is not going to change anything. Changing this number is not going to change anything. So what else is there? If we add or subtract a number, that's not going to really do anything. Again, that's just going to impact the size of the axes. The only thing that we haven't touched is this. What if we make that plus into something else? Now, had we the time, I would love to change that into a subtraction, into a multiplication, into a division, and see what weird things we get. But let's keep things simple. So we're going to pick the next most simple operation other than addition, that of subtraction. So I'm going to erase that. I'm going to make this subtraction. All right. This will not get us an ellipse. What will it get us? Well, let's find out. At first, let's start with our favorite number to plug in, that of 0 for x. All right, so if we put in 0 for x, we're going to end up with 0 over 9 minus y squared over 4 is equal to 1. This is all just going to be 0. Multiply both sides by 4. We get negative y squared is equal to 4. Multiply both sides by negative 1. We get y squared is equal to negative 4. Square root both sides to get y is equal to plus or minus, negative 4. The square root of negative 4, that is. So this will get us plus or minus 2i. That's weird. That's weird. We should not be getting imaginary numbers with these conic sections, which means that x cannot be 0. We've talked about this before, that if you're graphing something and you get an imaginary number, all that means is that that coordinate doesn't exist. So when whatever this ends up being, x cannot equal 0. We'll see if that what that looks like. So since this gets us an imaginary number, plus or minus the square, plus or minus 2i. Let's switch things up and let's start picking y's for this function. Let's try y equaling 0 as well, all right? I'm going to erase this. If we let y equal 0, we're going to end up with x squared over 9 minus 0 squared, which is just 0, over 4 is equal to 1. that all is going to equal 0. So we end up with x squared over 9 is equal to 1. Multiply both sides by 9. We get x squared is equal to 9. Square root both sides. X is equal to plus or minus 3. Okay, that's helpful. Plus or minus 3. Okay, so we picked a y, and that seemed to be more helpful. So I think we should kind of stay on that track. Let's pick another y. Let's pick some easy ones. How about 1 and 2? And I'm going to pause the video to just work out those. It's pretty straightforward. I'm going to have to talk a little bit more softly because I was falling asleep. So I worked out the algebra to get corresponding x's for y equaling 1 and 2. If you don't get these answers, I'm just going to walk through it real quick right here. Basically, that's going to become 1/4. Add 1/4 to both sides. We get 5/4 is equal to x squared over 9. Multiply both sides by 9. Square root both sides. The square root of 45 is 3 root 5, because 9 times 5 is 45. So separate out that 9 to get us, the square root of 9 is 3. So 3 times the square root of 5 over 2. The square root of 4 is 2. Which is approximately equal to 3.35. So that's just a little bit more than 3 1/3 for when we're graphing. Then over here, when y equals 2, we're going to get 4 over 4, which is just 1. So we're going to add 1 to both sides. We get x squared over 9 is equal to 2. Square root of both sides. Multiply both sides by 9 to get x squared equals 18. Square root of both sides. 18 is the same thing as 9 times 2. So the square root of 9 is going to be 3, and then the square root of 2 is going to stay because it's irrational. So we get plus or minus 3 times the square root of 2, which is approximately equal to 4.24. Okay, so this is good. This is not going to be helpful for graphing, but we have, let's see, 1, 2, 3, 4, 5, 6, at least 6 points we can graph, maybe more. In fact, there are more because 1 and 2 can be plus or minus because when they're squared, their being plus or minus doesn't really change. And I'm going to erase that. If you want to check that math, you can go back and pause the video. But let's graph these points that we have so far. So when y equals 0, x is going to be 3 and negative 3. And when y is 1, and also negative 1, we're going to get x equaling 3 1/3. So 3 1/3, so right around there-ish. And likewise for negative 1. And negative 3 1/3. When y equals 2, up here, x is going to be 4.24, so just shy of 4 1/4. So let's come up here. We're going to go to 4 1/4. So that's right about here. Okay. So this is looking promising. Likewise in this direction, 4 1/4. 2. Right. So this certainly looks hyperbolic. And by that I just mean it looks like it's going to be two curves opening in opposite directions. And if we were to take the time to pick some more x's and y's and fill them in, we could fill in these curves. I'm just going to go ahead and write this in. All right. And obviously these curves go on infinitely, but I'm not drawing them too much, and that's for a good reason. We'll get to that in a second. Excuse me. Now, before we move on, notice why we got an imaginary number over here. X, when we try to make x 0, we got an imaginary number. Excuse me. And we can see why. X equaling 0, it's not part of this graph at all. Neither of these curves cross the y-axis, so x can't be equal to 0. For that matter, if we try to let x equal 1 or 2 or anything less than 3, we're going to get an imaginary number. And you can kind of see that pretty quickly. Let x equal 1, right? Then 1 squared is just going to be 1 over 9. Subtract it from both sides, we're going to get 8/9 on the right side. No matter what that is, we multiply by 4 and we multiply by negative 1. We're going to get a negative number on the right-hand side, so when we square root, we're going to get an imaginary number. All right, so yeah, that's not going to work for us. We can, however, let x equal anything greater than 3. So just for the sake of completion, let's let x equal 4. We want 4. Let's pick numbers that are going to be easier for us. How about 6? Let's let x equal 6, right? Because that's going to be on our graph. Let x equal 6, and again, that's really going to be plus or minus. So if x equals 6, that's going to get us 36 over 9 minus y squared over 4 is equal to 1. 36 over 9 is going to be 4 minus y squared over 4 is equal to 1. Subtract 4 from both sides. We get negative y squared over 4 is equal to negative 3. Now we have a negative number on the right-hand side already, so when we get rid of this negative, that's going to become positive. Multiply both sides by negative 4, we get y squared is equal to positive 12. Negative 3 times negative 4 is going to be positive 12. Square root both sides. Y is equal to this plus or minus the square root of 12, which we're just going to say is plus or minus 2 root 3. And if I get my trusty calculator, we can approximate what that's equal to. Let's see. Square root of 3 times 2. Ooh. It's about 3.46. So plus or minus 3.46, which is approximately equal to plus or minus 2 root 3. All right. So enough on that. And now we can graph that as just one more data point. So 3.46. 3.46, that's just shy of 3.5. Ish. So we can continue our curve. All right, cool. So, it seems we've done it. We have generated a hyperbola. We've generated 2 infinite curves that go in opposite directions. And we got it from just kind of being smart about it and just predicting from what we already know. We know that the hyperbola has a lot more in common with the ellipse, and so just tweaking the equation for the ellipse just a little bit got us a hyperbola. But now the obvious question standing in our face is, what about the particular numbers that we picked, 9 and 4 as the denominators? Why did those numbers dictate what this looks like? I mean, at the very least, we can probably see that you'll notice that these 2 hyperbola are on the x-axis, opening left and right on the x-axis rather than the y-axis. And that probably is because the x term is positive, and then this one is negative. So I wonder if we were to switch those around and make it y squared over 4 minus x squared over 9 if we would get the same hyperbola but flipped, and we'll look at that later. So that's our conjecture for now. All right, and but why 9, why 4? Well, the square root of those two numbers is what dictated how long or short the major and minor axes were. We can kind of see already that we have something like that. The square root of 9 is 3, and these two vertices are exactly 3 units from our origin, right? So the square root of 9 seems to play a role, but why 4? The square root of 4 is 2, but I'm not seeing any 2's around here. So what role is that number playing? If that number was different, if it was bigger or smaller, what effect would it have on the shape of our hyperbola? That is a good question.